So thanks for joining me. Today I'm going to be talking about a tool that a colleague of mine and I wrote to facilitate fuzzing RF devices and protocols. Just to briefly introduce myself, my name is Matthew Knight. My day job is as a security engineer at Cruise Automation, a division of GM that's building self-driving car technology. Today I'm here to speak with you in my capacity as the RF principal at Riverloop Security, which is a boutique embedded systems and security consulting firm. I do a lot of RF reverse engineering, embedded device security, architecture design there. If you go back far enough, I got a BE in electrical engineering from Dartmouth, and most of my interests lie in software-defined radio and embedded systems. I want to give a shout out to my collaborator on this project, Ryan Spears. He couldn't be here today, but he deserves equal credit for all this work, so his name is still up there. The background behind this tool really goes back to some research that Ryan and some colleagues from Dartmouth did back in 2014. It was about fingerprinting physical layer, wireless physical layer protocols to find discrepancies in how manufacturers implement PHYs. I thought this was really interesting, so I kind of roped Ryan into getting on board to take this further, and we put together a tool that we call TumbleRF that is a fuzzer that can be applied to either physical or MAC layer technologies. And we're pretty excited with how it shaped up. We're using it in our own research to find more vulnerabilities, and I want to put it out there to the community in case it is of use to you and the applications that you might be pursuing. But I want to give credit to this, the Making and Breaking a Wireless IDS paper from 2014. That is really what preceded this, and it's a really good read. If you have cycles, I would go take a look at it. So we're going to begin with just a brief overview of fuzzing as it's applied to traditional software systems, and going to briefly comment on why it's hard to carry those methodologies over into RF or wireless domain. Then I'm going to talk about some kind of the state of the art, what's out there for RF fuzzing RF protocols. Then we'll go into some architecture, and we'll talk about the tool, and I'll end with a demo. So traditional fuzzing techniques. Just kind of sum up like this. If you haven't heard of fuzzing, fuzzing is basically the application of pseudo-random input to a system. So the idea is that you would monitor the state of the system while you basically inject data into it to try to identify crashes or odd behaviors within it. Because when you run into an odd behavior, that might be something that you can exploit. That might be a security vulnerability. Fuzzing also enables us to automate that. So rather than looking at the protocol, understanding it, having to think and be active about what we're trying to go after, here we can script it up, run it, go to lunch, come back, and look at the things that were interesting. So Fuzzer is generally attached to system I/O. So in software where we can control like the execution environment of the software, those are things like file format parsers, network interfaces, and in some cases shared memory. There are a whole bunch of really fully featured fuzzers out there that go after software currently. A really powerful one that seems to be popular these days is AFL, and there's also AFL Unicorn for going after firmware. But then we also have legacy fuzzers like Peach, and then also network packet tools like Scapy also include some fuzzing capabilities as well. Software in this case is very easy to instrument and connect to because you control the execution environment of everything that you might be looking at. But what else might we want to look at? So go through a couple other applications of fuzzing. Hardware is one where there have been some interesting approaches in the security world. And hardware is a little bit trickier to go after because these interfaces are often unique or less standard to hook into. And it might be hard to put together a test harness to measure and monitor the state of whatever device that you're fuzzing. But there are some existing techniques that I'll highlight briefly. So AFL Unicorn is a software fuzzer that you can use to simulate firmware, to fuzz firmware that otherwise would run in some sort of hardware architecture. Additionally, the devices, the bus pirate and the JTagulator, apply kind of like a fuzzing-inspired methodology to discovering RF interfaces. Basically, with those, what you do is you connect a whole bunch of wires to test points on a board, and then the firmware on the bus pirate or the JTagulator will essentially iterate through different pinouts and combinations to try to discover open debug interfaces. So it might say iterate through a whole bunch of baud rates and pinout combinations for RS-232 to try to discover an open or unlocked serial debug port, or it might try to push things through different permutations of a JTAG pinout to try to find unlocked JTAG chains. And those are the sort of things that you could do manually, but doing so is time intensive, is really tedious and not very fun. So these tools basically just kind of took a fuzzing-inspired approach and put some automation in place around discovering interfaces like that. Now, what if you want to fuzz RF protocols? There are a couple projects out there that I'll cite, and then we'll talk about why we wanted to build on these. The first I'll comment on is YFuzz, which is a 802.11 protocol fuzzer. It's focused on layer 2 and up, you can't really go after anything in the PHY, and it's also built up exclusively to target 802.11. So if you wanted to take this and say apply it to like, Bluetooth or LoRa or something like that, you'd basically wind up completely rewriting it because it's so built up around the 802.11 stack. I additionally want to comment on Mark Newland's mousejack research. Mark used fuzzing extensively in doing the mousejack vulnerability research a couple of years ago. And just to kind of sum that up, he looked at a number of wireless keyboards and mice. They used the NRF24 protocol, or chipsets and protocols, to communicate. It's kind of like a poor man's Bluetooth. And he used fuzzing pretty extensively in essentially generating test cases and injecting them at the USB human interface device that you plug into, the USB HID device that you plug into your laptop to try to get them into weird states or get them producing output. And he wound up not releasing his code for that, but it factored very highly into his research and resulted in something like, I think he had like 20 CVEs or something like that for, or 20 vulnerable vendors from that. So it was very productive. And additionally, I'll also mention the Isotope Framework that was developed as part of the 2014 Making and Breaking a Wireless IDS project that I mentioned. That was essentially applications of fuzzing to the 802.15.4 protocol, but as with YFuzz, that was very siloed, built up around that one protocol. So if you wanted to take it and apply it and extend it to work with another protocol, you'd basically wind up ripping it apart and rewriting it. So as I've kind of alluded to, there are some limitations with the open source projects out there for orchestrating fuzzing on RF devices and protocols. Generally speaking, they tend to be protocol specific, and they're generally limited to like the MAC layer and up. So if you want to go after physical layer characteristics, you're kind of out of luck. Additionally, just like instrumenting hardware, measuring and monitoring RF state is really hard to do. It's not like you're just like looking at the stack trace after a program crashes or something like that. It's really hard to know when you've gotten your baseband into a state that might be interesting. And additionally, when we're working at layer 2, as a lot of these existing fuzzers want us to, we're kind of trusting what the chipset gives us, which limits us even more. So if there are any weird things happening in the PHY or any like PHY fingerprints there that we want to go after, if we're trusting a COTS chipset, that might not necessarily give us the control that we want to fully exercise the protocol. So as I've alluded to, and as reported by the 2014 paper, not all PHY state machines are implemented equally, especially when you look across vendors. You might have a very well-determined and well-formed spec, but when vendors take that 3,000-page technical document and translate it into silicon, they do things differently. It's not even saying that they make decisions or they get things wrong. They might just based on the way they implement it might result in real differences in the characteristics of how the device operates. So again, more motivation for wanting to build a framework like this so that we can exercise protocols in an automated and extensive way. So I'm just briefly going to set up an example I'm going to be showing at the end of this talk, just to kind of frame what we're going to be eventually looking at before going into the architecture of the fuzzer. If you were at my GRCon talk last year, this might look familiar. Basically, what we're going to do is we're going to look at the 802.15.4 protocol, and we're going to essentially modify the preamble and the sync word. And the standard dictates that the preamble is 4 octets of zeros and that the sync word is 1 octet valued A7. However, if we, say, malform that and start speaking a dialect of 802.15.4 that's not standards compliant, say by not transmitting all all 4 octets of zeros in the preamble, or by changing the sync word, we might be able to find states where some receivers behave as expected and others don't. So again, more motivation for why we wrote this fuzzer. And obviously the power of this is that with fuzzing, we can automate discovery of this and hopefully make it rain bugs. So let's talk about the ideal design of the fuzzer, at least as kind of we conceived it. We wanted it to be extensible so that it's very easy to hook up new radios and protocols into this framework. We didn't want to wind up in a situation like we have with the current tools where if you want to take our tool and say fuzz Bluetooth, you have to rip out a whole bunch of assumed logic around a certain protocol to be able to support that. We also want it to be flexible so that you can so that you can basically tailor the test cases that you're generating to suit your application. Reusable kind of rolls into extensibility. We want it to be flexible and fit a whole bunch of different use cases. And additionally, we wanted to make sure that the PHY was exposed in a way that was coherent. So if you wanted to do any really low-level stuff, it would be easy to do. So that brings us to TumbleRF, which is the framework that we wrote earlier this year. It's open source on our GitHub. I'll have a link to it later. I'll just walk you through it briefly. So TumbleRF is a software framework that enables fuzzing arbitrary RF protocols. It basically abstracts away a lot of the core fuzzing logic, and it itself is just the skeleton that you need to stitch all these parts together. So when it comes to actually implementing a fuzzing scenario, really what you're doing is you're extending our APIs to map into your use case. So what we've done is we've abstracted the radio kind of on the device driver side, and then we've abstracted the test case generation on the host side, on the fuzzer side, and we've put together the skeleton in the middle that you need to stitch all that stuff together. So you can generate your own fuzzing cases in a way that's pretty clean, and also extending our radio API to match your use case is pretty straightforward. This is the architecture. I'll talk through the individual components, but essentially right in the middle we have this test case management class that hooks into test case generators and then produces output to a transmit interface. And then monitoring the state of execution of the device is a test harness that inherits the same class in which the transmit interface is built on. We'll go through this in slightly more detail. So the first thing I'm going to talk about is the interface API. And this is essentially the radio abstraction API that you would extend to map whatever driver calls correspond with the radio or device that you're going after up into our framework. And really there are only like 10 or 11 different functions you have to worry about here. Obviously get and set channel or frequency, start a frame delimiter and preamble if you're doing PHY stuff, and then we have commands for transmitting and receiving. It's very, very simple. The next class I'm going to mention briefly is the generator class. And the generator is essentially what produces an RF test case, and it does so in a kind of clean, Pythonic way. So basically, when you extend the generator class, what you're doing is you're writing in the logic that is actually going to produce the fuzzed out, or the input to the system that you're fuzzing. So typically, what that involves is instrumenting 2 cases. If you're doing things that are more stateful, you might have to implement this, implement more and have some more, case-specific logic. But kind of the MVP here is really 2 cases. The first is a control case, and the second is the actual fuzzing input. Now, why do we want a control case? Well, when we're fuzzing systems, we're trying to find weird behavior. That includes things like, crashes, packets being missed, et cetera. If we're just injecting test cases and we get a crash to happen, before we inject the next test case, we want to make sure that the device that we're testing is in a state that we know to be stable. So rather than like power cycling it or resetting it every time, what we do is we instead inject a control case after every test case. If that works as expected, we know that we're good and can keep going. If not, then we can trigger logic to reset the device, get it back into a known good state before continuing on with more test cases. So we have 3 generators currently. We have an 802.15.4 specific preamble length generator. We have a SFD generator as well. And then we also have just a uniform random data that we can shovel into layer 2 and fire off that's kind of generic and universal. But these are just examples. If you want to write your own fuzzing test case, you just inherit our base class, and you can write whatever logic in those functions you want. And finally, we have the harness. And the harness is essentially the part of the framework that monitors the device under test and looks for crashes or weird behavior. So generally, the harnesses they generally inherit the radio API interface. You might have say 2 instances of your radio, one that's doing the injection and the other that's under test. And that would be encapsulated within the harness. So we have a receive frame check, which is probably the most basic type, which is if you have essentially a radio dongle that you're able to read over serial. All that does is it calls into the driver and gets back a packet, right? So it's an easy way to check, did the radio that I'm testing receive a frame or not? If, say, you're running against like a dev board or something like that. If you're trying to fuzz a device, something that you don't have serial on necessarily, we have 2 other, or something you might not necessarily have, straight, the ability to query frames from. We have 2 other test cases that we're working on that we think are going to be really interesting once they're a little more mature. The first is essentially an SSH monitor. We're using the Python Fabric API. We can SSH onto a device and essentially run shell commands to monitor the state of processes on it. Obviously, that requires setting a shell on the device, but given that this is like lab security testing, we think that's reasonable. We also have a serial check as well, which uses an Arduino to basically stream back logs over a serial port. So if we can't, say, for instance, read the frame back over USB, we might be able to pull a frame out of a log that device might be generating and outputting over an insecure serial port. This is probably the hardest part of this, is finding different ways to instrument and monitor these devices. But we think we have some creative solutions here that get us part of the way there. So finally, we have the test case manager. And this is essentially the central block that coordinates all these things and does some central features like receiving data from the CLI, or receiving input from the CLI to kick off test cases, and also doing things like logging results. So basically, there's a base case called run test that you can inherit, and then you're basically extending the alternator to do 2 different things, which is closely related to what the generator is producing. So that's run the control case and then run the test case. And then the rest is just taken care of by the logic that we've written. So now that I've bored you to death with the software architecture on this framework that you haven't seen yet, I'll show a brief demo of us actually applying this. This is the 802.15.4 canned example that I showed last year. It's one that's public that we're willing to share at this point. And I'll just talk you through it briefly. So here's what it looks like. I've got a laptop that I'm running the host-based TumbleRF framework on. And then I have 3 different dev boards that I'm testing. I have an app emote that contains a TI CC2420 802.15.4 radio. I have a TI dev board that contains a CC2531 802.15.4 radio. And then I have an Atmel RZ USB stick, which contains the Atmel 86RF 802.15.4 chipset. These are all 802.15.4 standard chipsets, but we're going to essentially throw some different mutations of phi frames at them and see how they perform differently. And as a stimulus here, I'm using a B210. I'm generating data using a modified version sorry, I'm jumping ahead, but I'm using a modified version of GRCon18 802.15.4 written by Bastian that I've hooked into the fuzzing framework. So I can send data that I'm generating in Python in the generator into that, and it can essentially inject non-standards compliant dialects of the 802.15.4 phi at these devices that I'm fuzzing. So here we've got the RX interface encapsulated within the harness, as I mentioned. The RF between the TX interface and the harness obviously looks like a lightning bolt, because we all know that's what happens in the lab when you try to do things live. But essentially what this test case is going to do is it's going to iterate through different preamble lengths of the 802.15.4 phi. So we're basically going to take away octets and see if these chipsets are able to receive packets that use a non-standard 802.15.4 header. Here's the fuzzing test case input generator that I did in GNU Radio. Bastian did a great job of writing 802.15 GRIEEE 802.15.4. So it was super easy just to bypass the block that does the preamble. I believe it's the preamble, the SFD, and the length prefixing for this. So I'm instead generating that in Python, an environment that I control, and then I'm leaning on all of his good work for doing the rest of the DSP up to the USRP. So jump over and show a quick video of what happens, then we'll talk about the results. And just while I queue this up, wanted to say that when we did this talk at DEF CON, we opened up by letting this run for about 1.5 minutes, just to see what people would do, because we were conspiring a while ago, we were conspiring about what the most boring demo one could possibly do in any sort of tech talk would be, and we thought that live fuzzing would really take the cake. Literally just like watching software generate random input and see what happens is pretty dry. But we'll just watch this briefly, and you'll see how it works.
Did you win an award?
What's that?
Did you win an award?
People were amused, but yeah. So basically, initially it stands up the USRP, and then it just starts running through the different cases. We could run this a lot faster if we wanted to. There's just essentially a wait time constant that we can set in there. But then if you let this run for long enough, you'll get some results. We'll take a look at this in comparison with those other chipsets. So let's take a look at the results here. So we ran that test against all 3 different chipsets. And as you can see by what I've highlighted, we have 3 different chipsets made by 2 different manufacturers. Again, all these are implementing the same protocol, yet we have 3 distinct different behaviors on how they respond to packets with different, implementing different malformed dialects of this standard. So the CC2420 is very, very permissive. If you give it 1 octet of zeros, it will receive, it will receive it 90% of the time, right? It'll work most of the time. On the extreme opposite end of the spectrum, we have the Atmel 86RF, where it requires the 3 octets of zeros there. And then the CC2531 is somewhere in the middle. So, why do we care about this? What's the implication here? Well, say you are an attacker and you're going after a network that has some monitoring or logging on it. Maybe there's like a network coordinator that is logging traffic, or you have, say you're going after a 802.11 network where there's a device like a Cisco Meraki that has a security radio on it looking for all sorts of weird deauth traffic and things like that. Well, if you're able to fingerprint that chipset, you can then inject traffic at clients that the supervisor or the security appliance will have no ability to detect at all, right? It doesn't speak the language. As far as it's concerned, it's a completely different protocol. It will never register that this traffic was even there. So when the initial paper came out in 2014, I thought this was super profound. I'm excited that I was able to rope Ryan into working on this. We've been applying this framework to our own consulting projects, but we also are beginning to look at some other protocols as well, and the initial results are looking pretty interesting. So stay tuned, we'll be able to publish those at some point in the future. So if I haven't bored you to death and this is at all interesting, I would encourage you to grab the framework and give it a try. We would love to take your pull requests for different radio interface classes, different test case generators that you might be interested in, or architecture suggestions, things like that. Really, we're happy to have collaborators on this. Additionally, personally, I think that this framework could have applications that go beyond security as well. We obviously wrote this because we wanted to exercise this one class of vulnerability and see what else is out there. But I think a framework like this is perfect for doing conventional test orchestration. So say you're developing like a radio protocol or a product, an RF-based product, and you want to say have like a hardware in the loop test that you plug into your CI pipeline. You could take this framework and use that and almost turnkey use that to provide all the orchestration of the device that you're trying to test. It wouldn't necessarily have to be fuzzing. You could say, inject your own test cases against it. But this, I think, would do a lot of the legwork for the kind of more like run-of-the-mill test orchestration. Additionally, I think that this would be pretty interesting applied to other types of PHYs, hardware, things like that. We haven't quite gotten there yet. Right now, we don't have the abstraction in place to support that. It's all kind of built up around an RF paradigm. But it wouldn't take a lot of work to roll that back and make it kind of generic and applicable to hardware as well. So GitHub link is on top, riverloopsec/TumbleRF. Check it out if you're interested. And thanks very much. I'm happy to take questions with whatever time is left.
Thank you very much, Matt. We do have time for questions if anybody in the audience has questions. Raphael, does anybody have a handheld on that side? Oh, we have two over there. Okay. Yeah, Sebastian, if you wouldn't mind getting over to him.
So have you observed physical sort of like odd behavior beyond just like injecting packets that can't be seen? Do some devices actually crash when you inject certain malformed packets?
So to my knowledge, I don't think we've gotten devices into states where it's like unrecoverable or requires a reset. That would be like the holy grail, if you can break the firmware or like the state machine in a chipset. I think that would be really interesting. But I don't have any cases I can point to at this time.
Thanks.
So another question here. This is the 802.15.4. Have you done any work extending into other protocols?
Yeah, so we've started to look at other protocols. We're not at a point where we're able to talk about our findings or research there just yet, just because there's going to be some like disclosure involved there.
Well, to prevent duplicate work, then, is there anything you can say about what we should not want to work on if you've already been there?
Unfortunately, I'm going to have to say no at this point. Sorry, I'm sorry.
All right, can our next speaker go ahead and get mic'd, by the way? You can head back to the AV booth here. Sebastian, if you could get to Martin, and we got a question over here.
Yeah, so great talk, thank you. AFL has the concept of like, it's guided, so you're going to new states, and it sort of focuses more on those states that are new. Is there like a feedback mechanism in your harnesses that will say, hey, if it outputs, I'm in state 5 to, my serial output or something, can it focus more on like new states and try to discover new states?
Yeah, that's a great question. So right now, the fuzzing generators that we've written really are not that stateful. We haven't implemented any sort of intelligent logic like that. That would be very interesting to pursue going forward, especially for more stateful-based network conditions. Say if you have like a sequence of packets that you have to build up to get the devices into a state, that's the sort of thing where you could have like branching logic and feedback that could learn and become more intelligent.
Yeah, state explosion's a big deal in this space, So,
right.
Yeah, exactly.
Hey, Matt. Nice talk. I'm over here on your right. Hello.
There you are. It's a very, very wide room.
So I think it was Seth Heidfield, who's now with the Human Center, I think, or maybe he's not. I can't remember. He was actually trying to break GNU radio, so basically injecting RF signals that would break GNU radio. And I was wondering, it seems like TumbleRF should be able to do that as well, right? Just like have GNU radio as, not just as the stimulus, but also as the input. Would that be even like a sensible tool to do that? Or?
Yeah, absolutely. I mean, you could hook GNU radio using an interface or using the harness and use it to say find cases in out of trees that cause critical crashes or things like that. Could be interesting. At the same time, you could also just like, given that GNU radio is all in software, you could also just instrument it using a conventional fuzzer and provide IQ as the input to it rather than having to go over the air.
Yeah, okay. So it's probably not worth it then.
Yeah, I mean, it would be one way to solve the problem, but I'm not sure it's the most direct path. So. we had Ian just observe that pi bombs is an effective GNU radio fuzzing tool, which is cool.
Other questions?
Thanks very much, everyone.
We do have time for one more here.
Have you done any work integrating stuff like RFCat into it as one of the backend interfaces yet?
Yeah, so that's actually an interface that we've started to develop. We haven't released it yet just because it's not quite there. But basically the way that that works is you take our radio API that we've written and you just basically map the RFCat calls to do those functions into it.
So would it maybe make sense, building off of the other question about the test case explosion stuff, to have an engine that would then produce the necessary states to drive the RFCat in that desired manner?
Well, so that's basically what the radio API does, is it abstracts that away so that you can essentially reuse the test case generating logic across different radios.
Right, okay, so I definitely shouldn't submit a pull request that duplicates that.
Yeah, well, if you're interested, come chat and I can provide some more context around how it works. But I think what's there now will be pretty easy to map into what you're getting after.
Great, thanks.
Cool, thank you. And I'm around today and tomorrow if anybody has any more questions. So thanks
Thank you very much, Matt.
Great. Thank you.